Today I will show you an efficient alternative implementation for some common equation including delays. In the feature of the week number 26, we have explained how to use the delay function to implement delayed differential equations, DDEs. A typical case is a lifespan-based indirect response model. A population of cells, the response R, are described by cell production and cell degradation. The main assumption of this model is that a cell dies when its lifespan expires. This implies that the cell degradation rate is equal to the cell production rate delayed by the lifespan Tr. In this example, we assume that the drug affects the response via an Imax model on the production rate. The equation for the response is thus the production rate, which depends on the current concentration Cc, minus the degradation rate, which is the same term, except that we use not the current concentration, but the concentration that was present in the system a lifetime before the current time. So the concentration is delayed by a time Tr. Using the MLXtrand language, this model can be implemented using the delay function. The variable being delayed, here Cc, must be an ODE variable, so I cannot use the pk model macro to describe Cc. I need to write the pk model with ODEs. In this example, I will assume a two-compartment model with first-order absorption, for instance. The ODE variable Cc represents the concentration. The dose is added using the dpot macro, where I use the argument P equals 1 over the volume to transform the dose into a concentration added on the variable Cc. When the delay function is used, the set of equations become delayed differential equations, and this requires the use of a different solver. By construction, delayed differential equations are more unstable compared to ODEs, and the delayed differential equation solver is much slower than the ODE solver. Luckily, in many cases, the model can be rewritten to avoid the use of the delay function and stay with the efficient ODE solver. The key idea is to duplicate the ODE variables representing the pk, with one set being the actual pk fitted to the observations, and the second set representing the same pk but delayed. In order to delay the second set of ODEs, we simply administer the dose with a T-lag equals to the lifespan Tr. This does not require any change in the dataset. Each dose will be applied to both Cc at the time of the dose and to CCTR at the time of the dose plus Tr. Note that this solution of duplicating the pk only works if the equation using the delay, so here R, does not feed back into the variables that are delayed. This solution can be applied to many cases, for instance when you have a pk that impacts a PD. In this example, I have only one delay, but if I would need to delay Cc by two different times, for instance an initial lifespan and a modified lifespan, then I would need to duplicate the pk code twice. Once I don't use the delay function anymore, Cc and CCTR can also be computed using the analytical solution when applicable. For my two-compartment model, I can use the pk model macro, which leads to a pretty compact code. The idea is still the same. CCTR has the same parameters, but has a dose delayed by T-lag equals to the lifespan. Let's have a look at this model in MLExplore. In this MLExplore script, I have set up the option where I duplicate the ODEs for the pk. I have used ODEs because that's the most general formulation that works also for models that do not have an analytical solution. And when I generate the plots, I can visualize the concentration Cc, which is exactly the same as CCTR, except that CCTR is delayed by here 20, which corresponds to the value of the lifespan TR. And that's the response I can observe. To show you that the option using the duplicated pk gives exactly the same prediction as with the delay function, I also here have the code using the function delay, and I will plot both the response using the duplicated pk code and the response using the delay function on the same plot. So if I run this, I will change the color, and we can see that both are exactly on top of each other. Models implemented with ODEs run much faster than delay differential equations. Depending on the exact model and design, to run a fixed number of SAEM iterations in Monolix, the model using ODEs is 2 to 20 times faster than the model using the delay function. So the solution of duplicating the pk code in order to introduce a delay is very efficient in terms of computational speed and can be applied to many cases where delay is needed. Take care and have a nice week.